we continue with the discussion on the strain analysis. So strain analysis is important where you have deformation as an important aspect of your work. We have seen in the previous class what is the relationship between the displacement field and the strain field. So it is given in terms of the Cauchy strain displacement equations. So those 6 equations we have seen. So what we have seen is that if you have the displacements ux, y and uz, by using the Cauchy's strain displacement equation, you get the strain state at any point which is defined in terms of 6 strain components. So that is simple enough. If you know the displacement field, you can take the partial derivatives and obtain the strain field. So this is by taking derivatives. But suppose on this table I have put some load and applied strain measuring devices, what is called as strain gauges, and get the strain field in this particular table. And from that, I want to get what is the deformation. So you want to go reverse fashion. You will find that the problem becomes complicated. In that case, you have to integrate, start with 6 equations and return to 3 unique equations. So that requires a lot of adjustment, and it also gives us impression that these 6 components of the strain, they cannot be arbitrary. If you cannot assume any straight state at this point, and I cannot assume all strains at 0, and suddenly at another point I cannot assume all strains to be equal to 1. If you have that kind of arbitrary distribution of the strains, you will not be able to find the solution which conforms to the continuity of the material. Or if you consider a material which is continuum, that means there are no gaps, no cracks, the strain components, they cannot be independent of each other. So there is some relationship between the strains which ensures that what displacement solution you get is free of any voids or discontinuities. So for example, if you have some body which is having a crack, and if you pull this particular body, so before you deform, all points along this line are at one point. After you apply the load, the point which is at the same coordinate but on the left hand side will move on this side, whereas on the right hand side which move in the other direction. So one side it is plus displacement, another side it is negative displacement. So if you plot the displacement field for this particular plate, you will find that one side it is deforming something, another side it is, at this point there is a jump in displacement, and this kind of problems cannot be handled by the continuum mechanics that we have learned. So in order to ensure that this continuity is mentioned, you require certain kind of relationships. So that is called as the compatibility conditions, or they are also called as continuity equations. So we'll derive some of these equations in today's class, and then we understand the importance of this. Before we go into this, just to emphasize that any arbitrary strain field, if you assume, you will not get proper displacement, or in other words, there must be some relationship between these 6 components. We will take one simple example. So let's consider a small particle inside. So there is some body. I'm just considering one particle which is having height equal to delta y, length equal to delta x. Okay, we are just considering 2-dimensional wobbler. Let's call this point as point A and this point as point B. Now under the action of some loading, let's say the bottom edge, it extends by shorter amount. So the deformation at this point is shorter and the deformation at the other edge is longer. So that is what is the final deformed shape of this particular original rectangular shape. Will the strain be same at point A and point B? It will not be same because the deformations are different. So the deformation, the strain at this point, let's call it epsilon x, at point A, and this is epsilon V, epsilon X at point B. Now what would be the total deformation at this point? If the strain at point A is epsilon XA, how much would be this elongation? What is the basic definition of strain? The strain multiplied by original length of that component. So it would be epsilon XA multiplied by delta X. Similarly, the top edge displacement would be given as epsilon X B multiplied by delta X. Now you can visually see here that this body is not only elongating, but it is also getting distorted. So there is some shear component which is also coming in this particular component. And shear deformation or shear strength, they are always measured in terms of the angular rotation that is happening to the edges. So in this case, the angular rotation is given here. So this I am calling is a change in the strain in this particular plane. Since we are talking about xy plane, this will be gamma xy. And we are talking about from original strain to whatever small amount of strain is induced, I am calling it as delta gamma xy. So is this particular clear? So again, what we are doing here is we are trying to show that all these strain components, they cannot be independent. There exists some relationship between them. And with this simple example, we are trying to establish one of the relationship, and then we are going to generalize for any case what are the general relationships. Okay, so now if you look at this particular triangle, you can tell what is this delta gamma y, delta gamma xy. So that would be given by this distance divided by height of this triangle. So that would be epsilon x b into delta x minus epsilon x a into delta x divided by what would be the denominator, what is height of this triangle. So that is the delta y, the height of the triangle. So that is epsilon x b minus epsilon x a multiplied by delta x divided by delta y. By rearranging the terms, we can write delta gamma xy by delta x equal to, what is this? Is difference between strain between the bottom edge and top edge of this particular component. So that I am calling as delta epsilon x by delta y. So that is the relationship we got. So this is in terms of finite difference. If you tend the delta x delta y tending to 0, we can convert this into a differential form. And since both of these are functions of xy, it will be partial differentiation. So in the limiting case, we get the relationship that is gamma gamma xy by gamma x equal to gamma epsilon x by gamma y. So in this simple example, we have shown that the shear strain in this particular geometry, it cannot be independent of variation in the linear strain. So if the linear strain is increasing between the two edges by 10%, it automatically fixes or constrains the shear strain. You cannot have any arbitrary shear strain. The shear strain must obey what is the variation in epsilon x. So if epsilon x between bottom and top edge is certain, the shear strain automatically gets fixed, or change in shear strain automatically gets frozen. So that is called as a simple relationship. We'll see more general form. So this is for the simple case. We arrived at this particular equation, and after a few minutes we'll see that this is a special case of more generalized relationship, what is called as the compatibility equation. So any questions at this point?
I did not understand how we got delta gamma x.
Means how it is defined.
Yeah, defined also and that equation.
So delta gamma x is a right angle triangle. So delta, so actually, okay. So what you are saying is it is tan of delta gamma xy. Okay, so I just jumped one step. So can somebody tell why tan is equal to delta gamma xy? Because we are talking here about some small strain. So whatever theory we are doing in this course, that is called as a small strain theory. There is another theory called as a large strain theory, which is beyond the scope. So all those equations we are doing are in the small strain theory. Luckily, for most of the engineering applications, or majority of the applications, we are dealing with small strains. Unless you require certain, like springs and others, where you require large displacement, some other theory is required. But in general, most of the machine components which require strength as well as the rigidity, you will have small displacement. So as a result, this would be approximated as delta gamma x. Is that clear? Yes. Okay, so now let's make it a generalized form. What is the general relationship between these components? That's what we will try to establish. So for this, we'll take two of the Cauchy's or two of the definitions of the strain, and from that we get a general form of this equation. So I will start with the definition of epsilon x. How epsilon x is defined in terms of displacement, in terms of ux, y, uz. What is the relationship between epsilon x and ux, y, uz? Where ux, y, uz are the displacements at a point. I think batch A had done assignment just yesterday and batch del ux or ux my gamma x, epsilon y would be given as gamma u y by gamma y. These two equations are available to us. What we'll do here is we'll take second partial derivative of this epsilon x with respect to y. So that would be gamma y square and second derivative of epsilon y with respect to x square. So that is the relation. On the right hand side, the partial differentiation operator is commutative. That means you can change the sequence. Before taking gamma x, you can first take gamma y. So we can interchange the sequence of the operator. So we can write the first equation as gamma 2 sigma x epsilon x by gamma y square equal to gamma square gamma x gamma y. So what I have done here, I have just changed the sequence of operation. So earlier it was first with partial derivative with x and then 2 times partial derivative with y. I have just reordered them. I am first taking partial derivative with y, then again with y and finally with x. So this is allowed in the differentiation operator. So you can change the sequence. So I got these two equations. Now looking at these two equations, and the definition of the shear strain, can you tell what operations you can do on this equation in order to get some relationship which is similar to this? So just try to recollect what is the definition of shear strain. So you have equation number 1 and equation number 2. You can manipulate these two equations to get. Yes, we can add these two equations. So what we get is gamma 2 gamma x by gamma y square plus gamma 2 epsilon y by gamma x square equal to gamma 2 gamma x gamma y. So if you add these two equations, we get the form which is like this. And what is this quantity inside the bracket? That is the gamma xy. So what equation we get at the end of this? So this is called as the first compatibility condition. So through this equation, it shows that there is a fixed relationship between variation in epsilon x and variation in epsilon y with respect to variation in gamma x. So if at this point there is some variation in epsilon x, like we have considered here some variation in epsilon x, there cannot be any arbitrary variation in gamma xy. So that is what we found by simple geometry. In more general form, the general relationship between epsilon x, epsilon y and gamma xy is given by this particular relationship. So that is simply because of the definitions of the strains, which implies that the strains cannot be randomly chosen. They have to have certain interrelationship between them, and that is what is given by this particular condition. Depending on what starting point you consider, you will get two more set of equations. So we have considered epsilon x and epsilon y, and we got the relationship which is given there. If you start with epsilon y and epsilon z, you will get second equation. So what will be the second equation in terms of epsilon y and epsilon z? So if I am considering x and y, this is the relationship I get. If I start with y and z, what would be the equation here? What would be the first term? I am talking about y and z. Gamma 2 epsilon y by gamma z square. Here it will be z by gamma y square, and what will come here? Gamma yz, and denominator gamma y and gamma y. And similarly the last equation. So all these three equations, they are called as first set of compatibility equation. Compatibility means in order to have continuous displacement field, so if you have a body which doesn't have any cracks or voids, then whatever loads you apply, you get a continuous deformation field. So if I stand on this table, unless it is cracked, will get a smooth profile. So it will be smooth displacement profile, unless it is not continuum, if you have some crack in this table, you'll note that if you stand on this table, at the crack you will have discontinuity. So till the crack it will deform, and suddenly at the crack you will get jump in the displacement. So that unless that situation arrives, all the displacement and hence all the strains, they must follow a certain pattern in order to obtain a continuous or continuous displacement field. So this is the first set of compatibility equations. There is another set of compatibility equations which again can be derived in the similar fashion. It only requires 3 more steps. So that derivation we are not covering. So for this particular course, we are covering only derivation of the first set of compatibility equations, which is fairly simple. So you may be asked to derive any one of them. So whatever equation, so suppose you have to derive the last equation. So we'll start with what definitions? Epsilon x and epsilon z. So you have to just simply change it and you can derive this particular equation in the same manner. The full set of compatibility equations, which are 6 in number, is as given here. So this is the full set of equations. The first group is what we derived just now, so which is given here. And the next group of compatibility equation, it gives the relationship between, so here from shear strains on the right hand side, from the linear strains on the right hand side we have the shear strains. In the second set of compatibility, you are on the left hand side you have the different shear strains which are related to a particular linear strain. So again, starting with the basic definition of the shear strains, we can derive these equations, but that derivation we are not covering. If you can simply substitute the definition and calculate LHS and RHS, you will find that LHS equal to RHS. Okay, but this derivation we are not covering. You don't have to remember any of these equations. So if required, these equations will be supplied to you during the exam. But you should be able to derive the first set of equations. And more importantly, you should be able to tell what is the significance of this equation. So again, I'll repeat. So just mathematical angle is this equation that doesn't make any sense as an engineer. As an engineer, we understand that this is a mathematical model which tells us that in any body which doesn't have any cracks cannot have any arbitrary distribution of the strain levels. So if you put strain gauges on this table and if I plot the strain variation in all directions, and if I calculate these gradients or these partial derivatives is nothing but the second order slopes, they must obey these equations. If they are not obeying, that means this particular body has some non-continuum or it has some voids, crack or some problems are there. So that is what it implies. So all this mathematical, it symbolizes what is the physics of the problem and it gives in very compact form how the body should behave. So although it appears very complex at this stage, but this is applicable not only to this table, but is applicable to this bedding, it is applicable to the earth. So anything which is solid must obey this set of equations and this is called as a mathematical modeling of a system. So in this we are talking about any solid material. So any solid material must obey this set of equations. In general, in most of the engineering design problems, we start with displacement solution and then arrive at the strains. So in that case, when you are starting with displacement, if you look at the derivation of these equations, these compatibility conditions you don't have to worry about. So those become sort of passive. They will automatically get satisfied because you are starting with some continuous displacement function. So the compatibility equation will automatically get satisfied. But if you assume instead of displacement solution, if you assume the stress solution, that is in this table you assume that there is certain variation of the stress and then try to get the displacement, then this particular set of equations would come in picture. So their relevance is when you are doing trying to solve some problem where the displacement solution is not available but some other solution is available. So in that case you have to take help of these equations to constrain those integration. That is, you have to come backward from 6 component to 3 components. So you have to put some integration constants to establish that this particular equation will help you. We'll take one very simple problem based on these equations. So again I repeat, you don't have to memorize these equations, so don't worry about that. Okay, so in this case, somebody using some analytical model, so there are different techniques to obtain deformation of a body. So somebody has done some analysis and found out that in that particular body, the strain field is as given by this particular case. So that is what is given. We have to verify whether this solution is correct or not correct. The way to verify that is to plug in these values or these functions into the compatibility equations and check whether they are satisfying or they are not satisfying. So we will not verify all the equations, we will just satisfy the first equation which we derived today. So can somebody tell what is the first equation? Just read from your notebook.
Gamma square is gamma x square. Gamma square. Gamma x square.
Gamma x y what? Gamma x. Gamma y. So that is the first equation. You have to. Okay. So what is? So you have the epsilon x function is given there. So what is the value of this second derivative of epsilon x? So first you have to take derivative with respect to y. So gamma epsilon x by gamma x. So what is this value? To differentiate this function. The first derivative I am asking. Okay, sorry, here we are calculating with y. Okay. With respect to x it is 0. We require here with respect to y. Okay, so that is equal to p. And the second derivative, so that is equal to 0. Okay, directly tell me what is the second derivative for epsilon y. So that is the first derivative itself is 0. And the last one. So let's go step by step. So gamma xy by gamma y. So if we differentiate with respect to y, what you will get? It is px plus py, and you are taking partial derivative. So this is px plus py. So first derivative with respect to y will be p, and then you are taking derivative with respect to x of this, so that would be g. So you can see here that this equation gets directly satisfied. If you look at this function, all these are the first order function, so there is no product of x and y or yz whatever. and this is a second order differential equation. So it will automatically get satisfied. So any functions you use first order, these equations will always be satisfied. So in short, if your strain field is linear, the compatibility equations will always get satisfied. So that is what this particular course implies. Okay, so this is called the compatibility conditions or the continuity equations. And for T2 exam, your syllabus till this point. So that is what, yeah, T1 exam, yes. Okay, so I'm teaching about third year, so third year and for T2 you have got T1. That is, okay, so for T1 you will have syllabus till this point. You should be happy if the same syllabus is there for T2 also. It will be better. Okay, so before we close, I just want you to take through the question paper, because the T1 exam is the most important exam, in the sense that the more you score here, there is a less burden on you to clear the subsequent examination. So subsequent examination, the portion will be bigger or more complex. So this is where you are just having introductory components. So you have simpler content, smaller content. So score as much as possible here so that you don't have to struggle in the end sem. And again, the questions, those are there in T1 exam. The similar questions will be repeated in the end sem. So there are some topics like Cauchy's equation or the principal stress calculation. Those are the fundamentals. So those will be repeated again in end sem. So if you do it properly here, you are already secured some number of marks in the end sem as well. So we'll just see the last year's question paper and understand the pattern. So this is like in 12th standard or in SSC you have the coaching class. So understand the question paper and how to score. So I'm just moving from teaching solid mechanics to a coaching class where how to score the marks. So many of you may not need it, but there are certainly certain people who will need this kind of coaching or guidance of how to score. Those who don't need, will, with this helps, they can get 20 out of 20. So okay, so this is the end semester paper for the last year. So there will be some theory problems. So theory problems we'll discuss later on. First, let's see some standard problems. So as I said, assignment number 2 and assignment number 3, they are the most important because there are the numerical problems that you solve. Those will get repeated here. So if you look at question number 1C, you have been given the small, okay, here 1C. So you have been given the stress matrix, which is as defined here. Okay, in this question paper, this capital A, or in your question paper also, every person will get a different numbers in the exam depending on your last digit of your registration number. So this A is the last digit of your registration number. So if your registration number is 10, last 2 digits, then A equal to 0. If it is 19, then it is 9. So that is, and since it is numerical problem, for me I have to just run one spreadsheet and I get all the answers. So for me checking is not a problem. For you, if you want to practice, this question represents 10 questions. So there are 10 different numbers are available. Okay, so what has been given here? You have been given the stress state. You have to calculate the magnitude of traction vector on y plane. So can somebody tell how do you solve this problem? The first part. Okay, so you are now, assume that you are sitting in the exam hall and this question comes to you. So how do you solve it? The first part, the magnitude of traction vector on y plane.
We have to find have to find T and Y.
We have to find T and Y using the Cauchy's equation. So for that you require the direction cosines of the vector on the y plane. So that is the approach you have to take. There is another simpler approach. Just by looking at this matrix, so we said that each row represents something. So what does each row represent in this matrix? Okay, so that is the clue enough. So you go through your notes later on and find out just by observation can you solve the first problem. What you told is correct, so that is possible, but it will take a little more time. Here just by observation you can answer the first question. The second is a standard question, the magnitude of normal and shear stress on plane which is equally inclined to XYZ. So in the previous assignment, in each batch I have explained that this is one way it will come, that you will give what angle it makes with each of the plane, or you may be directly given what are the direction cosines, or you may be given angles which the normal vector with respect to plane. So prepare yourself for anything like this. So this batch was easy, so I had the same question as what we solved in the classroom. So for equally inclined, the direction cosines are 1 by root 3, 1 by root 3, 1 by root 3. So since it has come last year, you will not get the same. So you have to prepare something more. Okay, the second standard problem. So this question will come for 6 marks. So you should get full marks in this question. So do calculations with concentration and don't lose any marks for silly mistake. The second question is related to either principal stress calculation or principal strain calculation. So can somebody tell if the stress state or strain state is given? So let's consider the strain state. So in strain state, you have to first calculate the cubic equation. And what are the components of cubic equation? There are some invariants. So there are stress invariants. How many stress invariants are there? There are 3 invariants, which are in terms of the numbers which are given in this particular matrix. So you have to find roots of that cubic equation. That would give you the principal strain. And to calculate the direction, that is nx and y and z, you have to do some operation. Anybody recollects how do you calculate principal, that is the direction of maximum principal plane for maximum principal strain? So you don't have to tell the full solution, you have to tell the starting state. So from the diagonal term, you have to subtract whatever number you want to do, and then you have to proceed. And specifically in case of strain problems, there is some modification is to be done in these numbers. So what is that modification? No, subtract is there for both stress and strain. But in case of principal strains, there is a major difference with respect to principal strain. So what is that? Divided by 2 is correct. What you will divide by 2? Gamma. So all non-diagonal terms you have to divide by 2. Diagonal terms don't divide, and don't divide if the problem asked is principal stress. So principal stress, this remains as it is. Only principal stress strains it gets divided. Okay, this problem we just solved 15 minutes back, so you know how to derive it. So if you get this question, then you are lucky. If not, then you have to face something. And the last question, which is based on the strain displacement equation. So this is, if you refer to all past question paper, you will find that these 3 type of questions are always there. Even in NSEM, they will be always there. So prepare from them thoroughly so that you secure 10-15 marks in both T1 as well as in NSEM. Okay, how do you solve this last problem? So whatever is the multiplier for I bar, that is Ux, this is Uy, and this is Uz. And then you have to use those 6 displacement strain relationship to get the strain value. So in this case, only shear strain is asked just to reduce your computational time. But you may be asked, so pay attention what has been asked. If only one component is asked, only answer to that. Okay, so the question number 2, we are fully sick. Question number 1. So there may be some theory questions. So there can be variety of theory questions. So in this question paper, the questions are as given here. So it will be different every year. Every year there will be some different theory questions. So go through the theory question. In general, if you have paid attention in the class, you should be able to answer them. Okay, so that is it. Any other questions you are having?